Hello, and welcome to Do Dancing Clams. This is a Blender 3.4 tutorial demonstrating simple yet powerful node groups for creating animation from within geometry nodes. The first question to address is, why animate from within geometry nodes? And the answers are, for one thing, if you have sequences involving many moving objects, this can be very tedious to keyframe, and it also tends to be very inflexible once you're done. Also, if you are reusing objects across multiple projects files, it's easier to embed the animation sequences in the group nodes and pull those over as a unit rather than pulling over the group nodes and then having to refigure out the animation in the new project. So what these node groups do is they simplify the process of animation, they allow you to separate the animation logic from the mesh logic, and they also provide for parameterized control of animation sequences. This is one of the things we'll be working on here. And it's just a simple animated spiky ball. It's got a few of the points on the surface of the node being moved in and out, and it's also got a rotation going on. It's actually a fairly simple file, but it didn't want the animations for this to get too complex because I wanted to talk more about the nodes and less about a project file. Let me show you why I went down this road in the first place. This is the slinky that I created, and it was during the process of animating this that I lost patience and decided there had to be another way. I almost stopped the project at that point and just did conventional keyframe animation, but also I'm stubborn. So this slinky has just a few parameters to control its movement. It has the beginning of the curve and the end of the curve. It has a compression point or a decompression point, depending on how you look at it. So there's a point along the spring where it's maximally compressed and not compressed. And it also has a compression amount, which is kind of a subtle effect. And these things add up to animate the slinky around the edge of the object. This is a project I built up to show the difference between animation using these group nodes and traditional, let's say, math-based animation. So these are identical. One is animated using my new stuff. The other is accomplished using a more conventional technique. This is what I will call the conventional technique, and these are the nodes. Conventionally, you would take the frame, do a comparison between two different times, and that would tell you whether this block of nodes is controlling it. If they are, then you do some math. So in one of these subtracts, you'll get the total range. In the other subtract, we'll get where the frame is within that range. We'll do a division to come up with a number between 0 and 1. And this Boolean logic here, the AND, will tell you that, yes, the frame we're dealing with is between the points we're interested in this case, time 0 and time 1. And this all gets fed into a switch statement, which will output 0 if we're not, and it will output our interesting value if we are. And then so forth for the other two movements. So this is the first movement block. This is the second movement block. It's almost identical except for the time and what we're going to multiply the vector by. So this guy is just doing the y-axis. This guy is just doing the z-axis. This also gets fed into a switch statement. And then we have the third block of motion. Same sort of thing. And this also gets fed into a switch statement. And that gives us our motion. But you can see if you already have a complex geometry node setup and you start like throwing in a lot of logic like this into the middle of that setup, it gets really ugly. It gets really hard to tell what's going on, and frankly, you use a lot more nodes than you need to. In this new method, I'm going to create a cloud of points, and that point, there will be one point for every frame. Essentially, we are creating an array to store values in. What do we do with this array? This is the first node group, and by far the most complicated, but it's actually really easy to understand what it does. It takes a range as input, and it will output a Boolean telling you whether the current frame or index is within that range. It'll also output a factor between 0 and 1, and that factor is usually used to control some sort of math. So in this case, we're using it to put an offset along the y-axis. And then this information gets stored into our point cloud under an attribute name of our choice. And the same thing goes for the second movement, and the same thing goes for the third movement. And when we get to the end, so this is what we have when we're done. And I'm just looking at this pause here. This tells us where the ball should be offset to. And index 0 will correspond with frame 0. Index 14 will correspond with frame 14, etc. Then to control the movement of the ball, all we do is extract this attribute and use it to control the offset. So again, this is the old way, this is the new way. I talked before about how it allows you to separate the movement logic from the mesh logic. Let's talk some more about that. This is a Slinky group, and yes, I will be doing a tutorial on this. I'll just do it after I upload the project file with the group nodes in it, so I don't have to go through that information again. But this central part here, and don't really worry about what it is, this is the part that actually creates the Slinky itself. This zigzag over here, and it could be linear, I just wanted to stack it up. This is all the animation logic. And to use the animation logic, for example, we have a variable called curve start and curve end. That gets calculated over there, but to use it, we pull out the attributes by name, and we plug them into a trim curve start and a trim curve end. And all the other attributes that control the motion of the Slinky are similar. So you just have this very unintrusive single node that pulls out the value that you calculated somewhere else. And you can see over here, all we do is I basically block these up into the values I told you about earlier. So this is stretch position, compression amount, curve end, curve start. And if we look at this in the viewer, we see all those variables. So for example, at index 0, or what will be frame 0, we have a curve start of 0, a curve end of 0.1, so we're very close to the beginning. It's not compressed. It might seem weird that the compression amount is 0, but what it means is that the spring is equally tensioned all throughout it, rather than one part being more compressed than another. And lastly, the compression position, which is over as close to the beginning as we let it. And then as we go up in index, and again, this will correspond later to going up in frame numbers, these values start to change. So the curve end moves, the compression amount increases, and eventually the compression position moves to be closer and closer to the center of the Slinky itself. Let's take a quick tour of the actual nodes. So the index range node is the workhorse. It's the one with the most serious logic in it, but it's also, its job is very simple. So if we hook this up to the viewer, you can see what's going on. So in this case, I've asked it to start at index 6, loop around past 10, and end up at index 3. So index 6 is 0, 0.1, 0.3, 0.5, and then back around to the beginning, 0.6, 0.8, 1.0. It seems like a simple thing to do, but this is what you want to do at some point at the beginning of almost everything you animate. This flag here is a little bit interesting. And it, of course, it doesn't have to wrap. We could have just as easily done 6, and you see it goes from 0.5, 1, just like you'd expect it to do. The other thing we output is this Boolean, and you can see it is 0, where we're not in this range, 1 where we are. This allows nodes that take a selection. You can pop that right in here, and indeed, some of the nodes I created have that Boolean selection as well, that can be just nicely pumped into. This flag here is a little bit interesting. So there's 2 ways we use this. In this little dumb example here, we are creating a point cloud. So in this case, I want to have this driven by the index. Sometimes on simple animations, you don't want to deal with separate geometry to track all this. And in that case, just uncheck that, and now what's driving this is the current frame. So you can use this output and plug it directly into a subposition or something like that. As a matter of fact, we did some of that on here because the animation here is so simple, there's no reason to deal with the extra step of storing it in 2 points. Next up are some simple math functions. What these are designed to do is take this factor and to modulate it into different values. So if you want to take this linear factor between 0 and 1 and turn it into a cosine wave, you can, just by plugging it in there. Instead of a linear value, you get a building up in a curved way to 1 in the middle and then falling back to 0 at the end. These parameters allow you to control what section of the curve you're seeing. So if you just wanted the upslope, you could change the cycle count from 1 to 0.5, and then we would get the rise in a sinusoidal fashion from 0 up to 1. And a linear node does exactly what you expect. And the only reason this really exists is so you can change the scale from anything to anything. And really, you could also do this with a map range node or a float curve. I just included it for completeness. And lastly, there's a ping pong, which bounces from the beginning number to the ending number and back. This third group is pretty simple. You give it an attribute, and it'll store whatever you give it. So this just takes a floating point value and stores it in an attribute name of our choice. It seems pretty trivial. It gets less trivial when you hook up the in-range. So what this means is that we will only modify values that have this Boolean to be true, which means as we add values to control a variable along one part of our animation sequence, we don't have to worry about disturbing what we've done in other parts of the animation sequence. And this is the feature that saves us from the giant nested switch statements, because we'll take a more additive approach to creating the animation sequence rather than having to know everything all at once as the output of the last switch statement. Now let's make some nodes. First of all, make sure Node Wrangler is enabled. Edit, Preferences, Add-ons, Node Wrangler. Add-ons, Node Wrangler. And usually I turn this timeline window into my group node window, but this time I want to keep it, so I'm going to create a new window. And make this one our geometry nodes. Quick little bit of setup first. I want to set this to cycles. And under the output properties, let's go ahead and set this to 90 frames. Man, I wish Blender hadn't made 1 the default. Starting at 1 just ruins all math. I don't need the cube, but I do want a sphere. And make it all smooth. In the final animation, we're going to move out individual vertices to form spikes, but for now, I'm just going to move them all so we can see something happening. Let's grab the scene time and turn it into a number between 0 and 1. Divided by 90. And let's take this opportunity to go ahead and give ourselves a variable. Drag into space, select grouped input. This creates a new entry in our group inputs and also adds it over here. And make it an integer. This will run from 0 to 1. If I add 1 to it, it'll run from 1 to 2. And there we have it. Now let's take this stuff and replace it with what we really want. Control G to create a group. And I'd like to create all the inputs right at the top just to get it out of the way. We want a Boolean to determine whether we're going to drive this with the frame from the scene time or if we're going to drive it using the index of some geometry that this will be plugged into. We want an integer telling us what index is going to be the start marker. Another one telling us the end. And a third telling us the maximum. It's assumed that the end will always be less than or equal to the maximum. And if the end is greater than the start, then we just have a simple start to end ramp. If the end is less than the start, we assume that it wraps around at index max. And let's go ahead and take care of the outputs too. We want an integer for the index that's being output. So in the case of where you're using index as input, this is kind of trivial. When we're using the frame for input, this will be the frame we're currently on. This will be the total number of indices we're using. It'll be some math involving index end or index max. It's just handy to have this node do it for you. This is the all-important Boolean that says whether this index being output is within the bounds of what was specified in the input. And this is the factor, which is exactly the current index divided by the index count. So factor will always be a number between 0 and 1. And really, I started off by using these a lot, and it turns out over time, I've got to the point where I can't think of a case where I've used them recently. Almost always, the factor and the in-range flag are all that's really required. The first thing we need to know is whether we're being driven by index or frame. If the index of frame is true, then we will drive this using the true value, which means the index. If it's false, we'll be driven by frame. In the case of this example, we're going to be driven by the frame because we're going to use the simpler method of animation. There are two cases in this. There is the simple case where the starting value is less than the ending value, which means we're not wrapping past the end. And then there's the other case where we are wrapping past the end. We need to split these early. And you'll notice I'm using less than and not less than or equal. If the two are equal, I'm treating this as the case where it wraps all the way around. It could also be considered to have no indexes that are valid, but I figured the wraparound case is more useful than the trivial case. I'm creating two switch statements right off the bat. The one for float, this one is going to be our final output value for the current index, and the one in Boolean is going to be the one for the range. The logic used to derive these is the same. It's just that this will calculate a floating point value, and this will be true or false. I'm going to be doing a bit of this, duplicating the group input. This turns into such a tangle of noodle soup that it's nice to keep variables local to where they're going to be used so you don't have this crisscrossing mess of wires you're looking at all the time. So if our frame or index is less than the maximum and greater than or equal to the minimum, then this is in range. And so this is our in-range switch. Let's just call it that. If we are in the simple case, then whether this is outputting a 0 or 1 is controlled by this simple equation here. If we're in the wrap case, that'll be the false value, and we'll calculate that down below. So now we just need the value, which is easy. It's just the frame or index minus the start. So once again, in the case where we are in the simple case, the non-wrapping case, then these true values will come out these outputs, and the in range will come out of here, and the value will come out of here. We'll do the wrapping case separate, and they will be plugged into the false, the cases where this test here is false. And this will be our output. So now we have the value for the simple case, or the index slash frame for the index simple case. Let's calculate the index count. So we subtract the start from the end. If this is greater than 0, we're once again in the simple case and we are done. And that will be the number of indexes. If that is not true, then this is a negative number. We add it to the maximum, and that will be our total number of indexes. Now we want to calculate this factor here. And because if the values run from 0 to 1, I want both 0 and 1 to be included in the factor, I need to subtract 1 from the total number of indexes to include both bounds. So if this is correct, we should be able to use it to replace our original logic. factor, and we only want to do the set position if the values are in range. So now, not too impressive, but at least it works. But we can also play with the index n now. So now we've changed the range between 0 to 90 to 0 to 16. And then when we get to 16, fantastic. Now let's take care of the wrapping case. Now let's handle the wrapping case after a bit of tidying up. I'm going to create a box that adds 0 so it does nothing. The only reason I'm doing this is so that I have a labeled instance of what we're putting into all those equations. It just helps that makes noodles somewhat easier to understand. So there is 2 cases here that we care about. If the current indexer frame is greater than or equal to the start and within bounds, then it's part of our data set. If the indexer frame is less than the index end, then we also care about it. If it's between those 2 values, we throw it away. Let's get a copy of the group input. So if both of these are true, then this indexer frame is at the end and we care about it. The reason we add this test for less than index max is because we can't assume that the frame number will actually be less than that for many reasons. Subtract the index start to get the value. So when this is true, this will be our value. So the other case we care about is when the index or frame is less than index end. So if this is true, then we will pump the value we want to get out of this into the true. If not, we're just going to let the value stay 0. Now that value requires a little bit of calculation. We actually start counting at index start. So the distance between index start and index max has to be added to our value. And we'll just add the current indexer frame. I can collapse all these boxes because there's no hidden values in here. All the operations are labeled by the things they come from. So if we're greater than start, the value is driven by the top of this. If we're less than the end, the value is driven by the bottom of this. So this value is the wrap case. So it's going to be 0 or something else more interesting. So the true case for this value switch comes from the top, and the false case comes from the bottom. Now we just need to calculate the in range. And that's really easy. If it's in the top case, or it's in the bottom case, then we are interested. Now if this works, we should be wrapping now. So currently this expands from 0 to 16, and then stops. Let's change this to 30. So now we should start the expansion at 30, and we do. And we go up to the end, and then we wrap around back to the beginning, and then we stop at 16. Perfect. One last thing I'd like to put in before we leave is some bounds checking. When we calculated this value up here, we actually allow it to go beyond the end, which should not happen. If the indexer frame is out of range, then the value should always be 0. So this AND test here is to see if the value is within range, and if it is, we'll go ahead and use this value here, and if it's not, then we want to output 0. Somehow this got unhooked. Let's make sure this is all working before leaving this. So I'm going to create a point cloud to store these values into. It will be equal to the number of frames. We'll store a couple attributes in it. Bring up the spreadsheet. Control-Shift-Click to bring up the viewer. And we'll look at our points. Now we're currently in frame mode. So what's happening is this is pulling one frame, and that is driving these two things. So it doesn't really matter which point we're looking at here because they're all going to have the same value. So now our frame is 17. And as it crosses index start at 30, the in range gets set. You can see the in range value gets set and the factor starts to creep up all the way to the end, and then it'll wrap back to 0. And then when we get to 16, our value hits 1, in range is set, 1 more, and we're not there. Now if we change this over to index, we won't be driven by the frame, we'll be driven by the index value, and every point will get its own data. This is an easier way to tell what's going on. So now you can see in range is set for each index up to but not including 16. And it is also set starting at index 30 up to the end. And you can also see that the values start at 0 and they creep up to 0.787 at the wrap point. And then after we wrap, they're 0.8 all the way up to 1 at up to, but not including, index end at 16. So this means everything is working. This is also kind of a cool demonstration of the difference between the frame mode, which you can use for simple animations, and the index mode that's intended to be stored into points that you use for more complicated animations. I realize it's taken some time to get here, but I didn't want to rush through the index to range node because it really is the linchpin of everything else we're doing. For the rest of this video, and it'll be brief, I just want to finish up the Spikey ball demo and then one other demo showing how to use the attributes stored into a point cloud. So generally, for nice, smooth movement between two boundaries, a cosine works best. So let's put one of those in now. And we'll add a group for this. Control G. Now to control this, in addition to the factor, which is assumed to be a number between 0 and 1, so we'll want to provide the extents in case the user does not want 0 to 1 as the output. And there's no bounds on these. And the bounds on this will be 0 to 1, with 1 being a complete cycle. And I'm going to set 0.5 as the default. And we'll also have a number of cycles. We want to take this incoming number between 0 and 1 and multiply it by 2 pi, so that way the user doesn't have to keep track of radians. If we multiply the factor by our cycle count, that gets us our cycle count in radians, or our extents in radians. And we'll add in the offset, and that will do us from 0 to 1, but we have these values here, and we want these to control the actual range. Subtract them in from the max to get the range. We will multiply by the range and add in the value min. And also this number here, the output from the cosine is going to vary from -1 to 1. And I really want it to go from 0 to 1. So we need to normalize this as well. And actually the defaults will work. We want to multiply it by 0.5 to shrink the range and add 0.5 to bring it back to 0. And switch these. So what we want for these spikes is we want them to start with the same level as the rest of the sphere, and then contract, and then expand to greater than the normal size of the sphere, and then back to the rest position. And that's what we get here. So the -1 pushes the spikes in, the +1 pushes the spikes out, 0.25 starts at the position on the cosine curve when the output is 0. We just want one cycle. The spikes are easy to create. We basically attach a probability of each vertex being pushed away from the center. And that's too many. That's about right. And you can see how they go in for half the cycle and out for half the cycle. I love that. What makes this look not impressive is the spikes are all doing the same thing. So let's put a random probability on that too. We want one random value to control the start and another random value to control the end of each cycle. So this will control where each one starts. And this will control the endpoint. Use modulo because there's no point in having it be longer than the frame cycle. So now, spikes can appear at any time and disappear at any time. Lovely. Let's also give each spike a random length so they don't all go out to the same place. Just a little more randomness. Smooth this out and give it a texture. And how about just a couple more spikes? That's better. Yeah, more globby throbby. Love it. For the texture, we'll just do something really simple with glass. Like adding just a touch of metallic in and give it just a touch of color. And there we are. This is the simple animation process, where we use the frame input to directly drive the animation. Now I want to do a real quick example on how to do this with points. Let's get a new object. Doesn't matter what it is. Let's create our points to store the values in. I'm just going to force this to 90. And we want an object to manipulate. We're going to do two things. The first thing will take place between frame 0 and frame 30. And let's run the value between 1 and 2. And let's store this in an attribute. I'm going to Control G to create a group. This is going to be one of our store attribute groups. And as I said earlier, the important thing this node group does is it makes the storing conditional. So let's add a conditional for that. That will be a Boolean. So if the incoming Boolean is true, we will store the value. If it's false, we just want to read what the value previously was and stick it back in. I really wish store named attribute had a conditional on it, but it doesn't. And now let's duplicate this. Except this one will run from frames 30 to 60. It'll go from a value of 0.1 down to a value of 0.25. And we'll call this size. Now we need to hook up this in range, so the attributes will actually be stored. And this time we are not being driven by frame, we are using the index to put this value into this geometry. Let's create the thing we're going to be modifying. Now to make this work, all we have to do is fetch this attribute out and copy it into this scale. Control G to make a group. And the whole idea behind this design is captured in this node. So we take our attributes, we're going to sample the geometry that has the attributes in it, and we're going to use the current frame counter to summon the attribute by index. In other words, the geometry that holds all the values by index, we're going to copy them into the animation by using the current frame count. And let's go ahead and pass through the geometry too, so we can chain these. So we start at 0, the ball grows, and then shrinks according to the cosine curve. And then at 30, it shrinks and then grows again. And then at 60, it disappears because the default value for size hasn't been set. So it's 0 wherever we didn't set it. We can quickly add a default. So we'll just add another store value, have it be 1, so the default scaling is 1. And then we just click this flag, so it stores it everywhere. So before we do anything else, we just load up all the values with 1, and then these index ranges and the cosine values will change it to be something other than 1. And that's it for this video. I hope you enjoyed it. It was a lot of fun to make. It was a lot harder than I thought it would be, but the extra week was worth it. The project file is available on Gumroad. I strongly encourage you to get it. It's free if you don't want to pay anything. This will be the basis of the Slinky video that I'm doing next, and I'm not going to repeat any of this on the Slinky video. I guarantee you. Thank you so much for watching. I hope you enjoyed it.